Conceptual Introduction to Linear Regression, Part 8. An example in R with a binary predictor. Imagine I set up another simple experiment based on a math test like before, except this time people get a cup of coffee or a cup of decaf, and then they take a math test. There's no practice this time, just coffee. It's a binary manipulation. You either get the full caffeine content of the coffee, or you don't. As before, you can look at this code to generate and plot the hypothetical data if you're curious about it, but it's not the main focus of what I'm talking about. Here are the math test scores from this hypothetical experiment. On the left, the scores for people who got decaf, plotted in a semi-transparent gray so that overlapping points show up darker. On the right, the people who got real coffee. You can imagine calculating the means of these two groups. The one on the right will have a higher mean. And you might recall from previous stats classes that we could do something called a t-test to compare them. But we've already talked about a kind of t-test in this session, a t-test comparing a regression slope to 0. We can do that here too. Let me just change the x-axis. Currently it says coffee, and then on the left we have no, and on the right we have yes, as labels for the two conditions. Now, it says coffee, and we have numbers. But the two key numbers are 0 and 1. The data are still the same, but now, with numbers on the x-axis, the values are represented by numerals instead of labels. On the left is still people who did not get the real coffee, and on the right is still people who did get the real coffee. But now, instead of labeling those points as no and yes, I've labeled them as 0 and 1 on this number line. 0 means no, and 1 means yes. So do you like drawing lines? I like drawing lines. Why not draw a line here too? Just because they're categories doesn't stop us from connecting the dots. Sure, nobody got half a cup of coffee. Nobody got 2 cups of coffee. And it doesn't even make sense to have negative coffee, but none of that matters here. This line is just an abstraction. It's a representation of the difference between the two conditions that actually did exist in the experiment. No coffee and yes coffee. Let's look at the regression model output. Here's a regression model from R, and I just used the binary coffee variable with 0 as no coffee and 1 as yes coffee as the predictor in this model, with math test scores as the response. The intercept is 49.59. What does that mean? People in the no coffee or decaf condition scored 49.5 points on the math test on average. After all, the intercept is the estimated value of the response variable at the point where the predictor is 0. And here, the predictor is 0 for the no coffee condition. The predictor has only 2 values, 0 and 1, and the 0, 1 represents one of our 2 experimental conditions, and the response variable is the math test score. So this is the estimated math test score at the point in the no coffee condition. The slope is 8.01. What does that mean? It means that people in the coffee condition scored 8.01 points higher than people in the no coffee condition. After all, the slope is the degree to which the response varies along each unit of the predictor, and the unit of the predictor here is going from no coffee to coffee. That's what switching from a value of 0 to a value of 1 represents. As we discussed before, the computer got this p-value by doing a t-test comparing the slope to 0. And the slope in this case is significantly different from 0, which is another way of saying the difference between the no coffee condition and the coffee condition is statistically significant. It would be very unlikely to obtain a differential of 8 units or more between no coffee and coffee due to chance alone if the scores were completely independent of the beverage. So perhaps you've heard of a t-test before, an independent samples t-test, and you're used to thinking of it as a comparison between 2 means, where you take the difference between the 2 means, divide by the standard error of that difference, and compare it to a t-distribution with n-2 degrees of freedom. Student's t-test, named after the inventor's pseudonym. Here is the standard R function for that t-test, comparing the no coffee condition to the coffee condition. The t-value is negative 4.177 with 98 degrees of freedom, and the p-value is 0.00006. There's 98 degrees of freedom because the sample size is 100, and we've all been taught that the degrees of freedom for an independent samples t-test is n minus 2. The difference between the two means is 57.6 minus 49.6, those are the two means, which comes out to 8. Here's that regression table from the previous slide again in blue. The test of the slope is the same thing as the independent samples t-test. The slope, that is the difference between the means, is 8. Divide that difference by its standard error to get the t-value of 4.177 with 98 degrees of freedom, because the sample size was 100 and we estimated two parameters, the intercept and one slope, and 100 minus 2 is 98. The t-test of the regression slope is the t-test of the difference between the means. I don't mean that these things are similar, I mean that they are literally the same thing. So the lesson here is that we can get a lot done just by drawing lines. Here's the regression line again. The intercept is the point where this line is 0, the average value for the decaf group. The slope is how much higher the coffee group is compared to the decaf group. The line passes right through the means of both groups. In fact, it is defined in this case as the line that passes right through the means of both groups. Remember that the regression slope minimizes the sum of squared residuals. The mean is the point in a distribution that minimizes the sum of squared deviations from that point. So this regression line is just what we get by connecting the dots of the two means of the two groups in our experiment. And that's why the intercept is the first group, and the slope is the difference between the groups. And the t-test of the slope is the t-test comparing those two means. But don't get too bogged down in the examples. I'm going to do some more thorough examples next week. Right now, these are the main things that I want you to have in mind. We can learn a lot by drawing straight lines through data. When we fit a regression model, we have one response variable and one or more predictors. Given this information, the computer finds an intercept and slopes for each predictor, making an equation like this. The actual values of the response variable will differ from the fitted values that you get from this equation, and those differences are called the residuals. The linear regression algorithm identifies the unique intercept and set of slopes that minimize the sum of squared residuals. The LM function in R fits this kind of model, and we're usually most interested in the slopes for each variable, typically denoted with the letter B, sometimes with a Greek beta. A positive slope indicates a positive relationship between the predictor and the response variable. Higher values of the predictor go along with higher values of the response, and lower values of the predictor go along with lower values of the response. A negative slope indicates the opposite, a negative relationship. We get p-values indicating whether these slopes are different from 0 by a margin greater than would be expected due to chance alone. Adding or subtracting constants from the variables does not change the nature of the observed relationship. It just changes their reference point. Multiplying or dividing by constants does not change the nature of the observed relationship either. It just changes the units of the variables. And if you have one predictor and one response, and you standardize or z-score both of them, then you get the conventional correlation coefficient as your slope. And all of the rest of the aspects of the regression model will be the same, because standardizing a variable is a result of subtracting a constant and then dividing by a constant. As the name implies, this kind of regression, linear regression, constrains the described relationships to be linear, straight lines only. If the pattern in the data is not a straight line, or at least close enough to a straight line, then this approach might be inappropriate. But this tool is incredibly powerful. Some of you might use it in one form or another to analyze the results of most of the experiments you will ever do. We're going to spend the next several weeks talking about all the increasingly sophisticated ways that you can put linear regression to use in your research.